Rick, we're going to spend some time asking how we can figure out the direction and the magnitude of magnetic fields caused by currents. And there's something called the right-hand rule. In fact, Connor, there's 3 of them. So you want to find where we are right here. Those people that are away today picked a bad day to be away because this is almost impossible to learn from YouTube because it's going to be very visual. Ooh, someone's phone just went off. Taylor?
Sorry.
No, Timbits.
So it was unlocked.
Pardon me?
It was unlocked in my pocket.
Timbits. Excellent. Need that. Electromagnets. Read along with me. It says this. A current carrying wire generates a magnetic field. In other words, if you put a compass near a wire, it will be deflected if that wire is carrying current. And the question we want to ask is, what direction is the magnetic field created by a current carrying wire? So I'd like you to look up and I'd like you to imagine that this meter stick is a piece of wire. Okay? I'd like you to look up and imagine that this meter stick is a piece of wire. Connor, I'm talking to you. I'd need you to look up. Have you found the notes? Yeah? Okay. Can you put whatever else that is away? Thank you. This meter stick is a piece of wire carrying a current. And let's pretend the current is moving to my left, your right. All right? What you do is you hold the wire in your hand. You point your right thumb in the direction of the current. Your fingers curl in the direction of the magnetic field. So above the wire, on top of the wire, the magnetic field is pointing towards Pierce. In front of the wire, the magnetic field is pointing straight down. Beneath the wire, the magnetic field is pointing towards me. And behind the wire, the magnetic field is pointing straight up. If the wire was running vertically like this, and if the current was going this way, I would point my thumb like that. Now I'll remove this. And so closest to Pierce, the magnetic field is pointing towards Josh, to your left. On the left side of the wire, the magnetic field is pointing towards the front of the room. Now I got to go this way. On the back side of the wire, the magnetic field is pointing to your right. And on the right side of the wire, the magnetic field is pointing right now towards Mackenzie, or right now towards Paul, or right now towards Josh. Okay? There are 3 right-hand rules. This is the first one to help you figure out the direction of a current carrying wire. So here's a question, example 2. It says, sketch the magnetic field. Here's a wire. We're looking down the end of the wire. Which way is the current flowing? What does that X mean? Into the page. So all of you right now are going to take your right thumb and point your right thumb down into your page. You're going to point your right thumb down into your page. Curl your fingers. Which way is the magnetic field going around this wire? Is it going in that direction or is it going in that direction? Is it going clockwise or counterclockwise? So if we wanted to sketch the magnetic field right now, you can draw a little circle like that, and then you can put arrows going that way. Using your left hand. It has to be your right hand.
Yeah, no, I was just
Don't do that.
kidding.
Don't do that. I have kids that do that sometimes, and they forget. Here's a picture. This is the wire. Thank you. What's a capital B an abbreviation for? Okay, so we need to know that. Absolutely, we need to know that. We said that we're going to abbreviate magnetic field with the letter B. We can't use M. M is taken already for mass and other things. So we're going to be talking about a B field. When you see a capital B, that's magnetic field. Oh, and it's measured in Teslas, for those of you that were away. So, which way must the current be flowing in that wire, to the left or to the right, to create a magnetic field? What do those dots above the wire mean? What direction is the magnetic field? Out of the page? What do those X's below the wire mean? So instead of using your paper, let's all use this screen right here behind me. So you're either going to point your thumb that way or this way? Right thumb that way. Get your right thumbs out, Rick. Get your right thumb out, Connor. By the way, you want to do this wrong? Do it in tight, Connor. Don't do it in tight. Get your hand out. Trust me. Talking to you, okay? So you're either going to hold your thumb like that or like that. Is the current flowing to the left or to the right? Which one gives you the magnetic field that I've drawn? Is current going to the left or to the right? Which one gives you the magnetic field that I've drawn? Josh? There's no bottom one. We're looking for the left. Hold your hand out. Get your elbow off the ground. Hold your hand out. Right thumb. Point. Connor, you too. Everybody. Okay? You have to participate or I'm going to get angry at you. If you point your fingers to the left, with your thumb to the left, which way are my fingers moving above the wire? Which way are they pointing? Into the page? See it? Which way are they pointing beneath my thumb, beneath the wire? Out of the page? Is that what we see there? Is that what we see there, Justin? No. What do those dots mean? So, try holding your thumb this way. Which way are our fingers pointing now? Above the wire, they're coming out of the page, and beneath the wire, they are pointing into the page. Josh, coming back to you. Which way is the current flowing in the wire? To the left or to the right? Let's circle this arrow here. The bottom one. Not even an option. Now, this right-hand rule works for positive current. If they're ever asking about electrons, you got one option. You got two options. You can either use your left hand. I'm not a fan of that because now you're learning another rule. Or you point your right thumb in the opposite direction that the electrons are moving. An electron moving south is the same as a proton moving. Electron moving left is the same as a proton moving. That I find is far easier, and then you're just reinforcing the right-hand rule. Okay? So I prefer this method here. Here's a picture of the right-hand rule that I found online. So if you have a wire that's carrying current, you point your thumb in the direction of the current, and your fingers, Deanna, tell you the direction of the magnetic field. That's which way a compass would point. That's right-hand rule number one. Okay? You guys with me? So here's the current going this way. So the magnetic field points like that, points like that, points like that. We'll practice this some more. That's one wire. What if you combine wires? In fact, what if you take a wire and you wrap it around and 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 around? We have a name for this. We call it a solenoid. A hugely useful electric device. Here is a solenoid. Although this isn't a very strong one, there's massive gaps between the wire. Here is a better solenoid because the closer you cram the wires together, the stronger the solenoid will be. This will form a magnetic field much stronger than a single wire because all the magnetic fields that are wrapped around will overlap and strengthen each other. And so the question we want to ask is, what direction will the magnetic field generated by a solenoid be? It's a good question. Here's a typical solenoid. Also, we have learned that if you put an iron core in the center of the solenoid, it dramatically increases the strength of the electromagnet because that piece of iron gets magnetized as well and adds to the magnetic field. Solenoid has thousands of uses. We use solenoids in... do I have a little rant here? I do. Good. I'll go on my rant later. Here is the right-hand solenoid rule. I'm going to pretend this is a solenoid because a solenoid is always cylindrical. What you do, look up. Bryce, look up. Folks, I need you here. You imagine holding the solenoid in your right hand. I can either hold this like this or like that. Okay? You're not going to hold it sideways. You're going to hold it comfortably in your hand because it's cylindrical. You look at the current that's running through the wires You look at the direction of the current that's running through the wires. You curl your fingers in that same direction. Your thumb points north. Your thumb points north. We're going to do a bunch of these, but this is the right-hand solenoid rule. Again, let me emphasize, if you try doing this in tight and close, you're going to get it wrong. If you just watch and don't participate, you're going to get it wrong. If you foolishly bring in your left hand, don't do that. Don't even try and reinforce that. Okay? So, example 4 says, what direction is the magnetic field below? I didn't even give you a solenoid because I also want to teach you how to draw a solenoid. I just gave you the iron core that we're going to wrap it around. So do me a favor, please. Put a battery right there. Connor's figured out where we are now?
Yes.
Okay. And we're going to have the wire go like this. We're going to have it vanish behind the solenoid. And then just look up for a couple of seconds. To give the illusion that this is a nice three-dimensional picture to make a solenoid, what you do is you go long, elongated S's. So if you want to draw that as well, and it's like a stretched out letter S, or a reverse letter S, depending on how you draw these. There's a solenoid. You don't have to have the same number of S's as me, just a bunch. And can you see, that does kind of look 3D-ish. That's about as good as I can draw these, but that gives the idea. Once you finish drawing these are the pictures that I'll be giving you. We're going to then draw in the current. I'll change colors. The current flows from the battery that way. It looks like it ducks behind. And then if you use your imagination, can you see, Kiana? I think it must come over the front like this. Yeah? So we're going to again use my screen as our piece of paper so that all of us are looking at the same idea. It seems to me I can either hold this solenoid this way or that way. I can't hold it this way because that's not the direction that the solenoid is aligned. Hold it in your right hand using your imagination in such a way that your fingers curl in the same direction as the current. And I think all of you realize you have to hold it with your thumb pointing in which direction? That's going to be the north pole of this electromagnet. That's going to be the south pole. That's the right-hand solenoid rule. If we now go back one question to right here where it says a typical solenoid, mine is in green, yours is not. Can you find this one here where I first gave you the solenoid picture? Got it? I'm going to label the current. Current goes from positive to negative. It's a bit tricky because yours didn't photocopy great, but when I zoom in on mine, it looks like I think the current is going that way. Is that okay? So hold that solenoid, imagine holding that solenoid in your right hand. You can't hold it that way, Connor. Oh, well, your piece of paper, the way you have it aligned, sure. I would hold it like this. Oh, wait a minute. If I hold it with my thumb pointing up, can you see my fingers are curling the wrong way? I have to hold it this way. Right, Emily? Yeah. And so that would be the north pole. That would be the south pole. You want to flip the magnet, flip the current. This idea of a magnet that we can turn on and off, hugely, hugely, hugely useful. What did we have yesterday during Flex? Looking for the letter F. Fire drill. The fire alarms are a classic example of a solenoid. My friend lives in a very, very old building, and when I was in his building, I went, oh, this is great here. I could see the solenoid. So there's the solenoid right there. This is his old fire alarm. And all that they have right here is this little piece of metal has a permanent magnet on the end of it right there. and they're running alternating current through the solenoid, so the magnetic field from the solenoid does this, does that, does this, does that, oscillates, which means it now pulls this little magnet on the end of this piece of metal back and forth, back and forth, back and forth, which if you follow that would make this little piece of metal go back and forth, ding, 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 ding. All our fire alarms work the same way. All they've done is they put this inside the bell so kids can't vandalize it. Really, anything in the old days that ever rang, that was a solenoid inside there. I think your smartphones, the vibration mechanism, I think it's a solenoid, but I think it may vary from type to type and brand to brand. They're used all over the place. Power door locks, when you make the locks go forward or back, when you lock the doors, you're turning a magnetic solenoid on and off, and it's either sucking the lock in or repelling the lock out. Piece of cake. We use solenoids all over the place. Hugely useful. So we had right-hand rule number 1 for a single wire, the right-hand solenoid rule, right-hand rule number 2 for a coil of wires. I'm going to skip example 5. I'd like to do it, but I'm going to skip it. Try example 6 on your own. Which end of that will be north? What's north, A or B? Let's see. If A is north, that means that I curl my fingers this way. Look at the arrows. Which way is the current coming? I think the current is coming towards me over the top. Is it not? Yeah, north is B. Look at your fingers. It's B. It's B. Okay. By the way, here's really what's going to be happening. What we're finding is the magnetic field direction outside the solenoid. So outside the solenoid, a compass would point that way. A compass would point that way. Inside the solenoid, a compass would point that way, because magnetic field lines are, I can't call them circular, they're not even elliptical, but they have no beginning and no end. They keep going. Okay? Those are the 2 easy rules. Sorry. The third rule is called the right-hand motor rule. It's called the motor rule because this is going to explain how electric motors work. It's also going to explain how electric generators work. Suppose we have a wire carrying current through a magnetic field. Everybody draw current in on the wire. I looked at the battery and I said, oh, that's the positive end, so the current must be going to the right. Taylor, draw that in. That wire will generate a magnetic field. If you put that wire, which is generating a magnetic field, into an external magnetic field, those 2 magnetic fields will interact and apply a force. Okay? Those 2 will interact and they will apply a force. This wire will feel a force. Now, this picture here, then, I have the wire, and this right here is meant to be the magnetic field. What do those dots mean? What direction is the magnetic field that this wire is in? Out of the page. Okay. The current is going to the right. Dots mean out of the page. Tail feathers, X means into the page. All right. To find the direction, all of us, we're going to use this diagram, and then we'll start doing it on our own piece of paper, but so that we're all the same. This is by far the most complicated one. Put your pencil down, Rick. Get your hands free. It's another right-hand rule. Here's what you do. Step 1, point your right thumb in the direction of the current. Except you're going to hold your hand like you're about to high-five somebody with your thumb out. So not a high-five like this, a high-five like that. Okay? And you're going to keep your hand locked like this. So you're going to point your right thumb in the direction of the current. You're going to point your fingers in the direction of the magnetic field. Which way is this magnetic field? For all of you, it's forwards. Yes? on this screen here, sorry, out of the page, like this. I apologize, I read that backwards. For all of you, it's out of the page, yes? And so we're all kind of bending, a little yoga here. Your palm points in the direction of the force. Which way is my palm pointing? Down the page. This wire will feel a force down the page. We're going to do a bunch of these. Okay. Oh, there it is. The net force would be down the page. So I wrote here, to find the direction of the force, you point your thumb in the direction of the current. Your finger is in the direction of the magnetic field. Your palm pushes. I always imagine that my palm is applying the force. There's another way to do it. You'll see some textbooks, they use thumb, index finger for the magnet, and then middle finger at right angles to do the force. My problem is my middle finger doesn't want to quite bend. I got this weird wonky thingy. I just can't do that one. Whenever I try bending one finger, this one wants to come in, and I can never form the perfect right angle that the books seem to suggest. So mine is high five, thumb out. Thumb is current, finger is magnetic field, palm is force. Example 7. Here's one. Let's decipher this diagram. See the wire? Which way is the current flowing? What does that X mean? Okay, so you're going to do this one on your own piece of paper. Right now, all of you are pointing your right thumbs into your piece of paper. Put your pencil down. Yep. By the way, you can't do these holding a pencil in your right hand. You got to clear your hand. What direction is the magnetic field? Look at the arrows. What direction is the magnetic field, the B field? Just tell me, please, so that we know. To the left. So somehow, with your hand like this, you're going to go thumb into the page. Now, you got a couple options. If you're flexible, you can kind of do that. Yes, if I'm doing it your way, so let me stand relative to all of you. So if I'm doing Connor, I could do that. Or, if it gets really awkward, rotate your piece of paper by 90 degrees. Or rotate your piece of paper by 180 degrees, because it'll still work as long as you adjust the direction. Okay? Which way is your palm pointing? Now, if you want to do it up here with me, if you want to lift your piece of paper up and hold it up with your left hand so it's vertical, so that it matches my screen, we would go like this. Thumb into the page. Magnetic field. Now, I have a tough time bending like this. Look up, look up, look up, look up. I can do that really easy, though, so just, if you have to, shoot your hand across your body. That's not correct. That can't be correct. Stop. With your left hand, hold your piece of paper up vertical. Vertical. So it matches my board. Okay? So, thumb into the page. Fingers like, I can't quite bend like that, so I just shoot my hand across. Which way is my palm pointing? Which way will this wire be deflected? Up the page. On the old physics provincial, there was always about 4 or 5 right-hand rule questions. In my first year teaching Physics 12, the students were all writing in the library, and I wasn't allowed to be in the room. And partway through the exam, my phone rang, and the librarian who was supervising the exam just sounded terrible. They sounded like just in agonies. Mr. Dewick, I know how much you like your students. You're going to be so disappointed, Mr. Dewick. They're giving each other coded hand signals. They've worked out hand signals, and they're passing answers back and forth. And no. So from then on, I explained to everybody supervising the exam, look, about an hour into the exam, you're going to see kids doing this. They're not giving each other hand signals. They're using the right hand. There's just no other way around it. Put your pencils down. Example 8, we're going to do a whole bunch of right-hand rule questions really quick. Boom, 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 boom. An electron traveling to the right, we don't do electrons. Our right-hand rule works for protons. An electron traveling to the right is the same as a proton traveling which way? So point your right thumbs to the left. It enters an external magnetic field. What do those X's mean? Which way is that magnetic field? Into the page? Which way will the electron be deflected? I'll give you a hint. It's either going to get deflected up or it's going to get deflected down the page. So let's see. If you want to follow me up here, you can hold your paper vertically next to so that it matches my board. Or if you want to try these on your desk, you can. But I would go, okay, magnetic electron traveling right, proton traveling left, magnetic field into the page. Which way is the electron going to get deflected? Down the page. Example 9, here's a bit more of a three-dimensional picture. I find three-dimensional pictures are tougher, but we can handle it. Is it an electron or a proton traveling? So we're going to point our thumbs in that direction. Wait. They didn't tell me the direction of the magnetic field. Or did they? Magnetic field lines always point from what to what? So right now, and I always do this, draw in with your pen or pencil, draw in magnetic field lines. And they point from north to south. This is a bit tricky, but I'm going to do mine up here. So I have the proton traveling this way. Magnetic field lines from north to south. Oh. What's the correct? You were holding your hand like this. Proton traveling this way. Magnetic field lines from north to south, Taylor. So using your piece of paper, so on your piece of paper, let me line it up. Let me see your picture. You would go like that and like that. Or you're turning your paper. Okay, then I won't, because I was just watching your alignment and it was wrong with everybody else. But if you spun your paper, that's different. A, B, C, or D? A, B, C, or D? B? Is that what you said? Example 10. The above diagram shows an electron traveling to the right. We're not going to do an electron traveling to the right. What are we going to do? A proton traveling to the? Okay. In a magnetic field. Oh, I don't see the magnetic field. Magnetic field lines always point from what to what? Draw it in. So, if I was staring at my handout, and I'll face myself so I'm in the same direction as all of you, I would say proton traveling to the left, magnetic field line. This is a bit awkward because the magnetic field lines are going down the page. I've got to kind of bend my hand like that. But what's the correct answer? I think it's B? Yeah? Yeah. And again, if you're bending awkward, Devin, like this, do that. Or spin it. Like honestly, I'd probably spin it like this and I would say, oh, that's much easier to hold the paper this way and bend my arm around or whatever. Okay. So what do we say? B? Which of the following diagrams best illustrates the magnetic field lines around a wire carrying conventional current in the direction shown? Okay. This is not what we've just done. There is a wire, but this wire is not going through an external magnetic field. It's asking, what magnetic field is the wire creating? What was that right-hand rule? That was the first one that we learned. You imagine you're holding the wire in your hand. That's right, Josh. You point your thumb in the direction of the current. What's that dot mean? The current is coming. So I'm going to put my thumb pointing out of the page. My fingers curl in the direction of the magnetic field. Mackenzie, what's the correct answer? A, B, C, or D? C? Put your fingers, go like this. So what's the correct answer? Yes, A. By the way, what you're really doing, and I haven't told you this, Mackenzie, with this right-hand rule, we're doing three-dimensional vector multiplication. How do we add two vectors together? Draw them. How do you multiply two vectors together? There's two different methods. One's called a dot product and one's called a cross product. And in a cross product, That direction cross that direction is that direction. That direction cross this direction is that direction. It's how everybody does it. Your right-hand rule is a cross product. Also, this is also a torque. If you're ever using a screwdriver, if you want the screw to go in, you turn the screwdriver that way. If you want the screw to come out, you turn the screwdriver that way. The current magnetic field rule also works for torque. Little nerd trivia. Oh, I just blew Kiana's mind there. It's how I do it to this day. When I can't remember which way I'm going to turn the screwdriver, I want the screw to go that way. The screwdriver gets turned this way. Example 12. Ooh, this is the solenoid rule. I better draw in the current very carefully, Deanna. So the current goes like this, and then it looks like it ducks behind. And do you agree with me? I think it's coming like that on the front end towards us. The current is pointing up. So imagine you're holding the solenoid in your right hand. You can only hold it this way or this way. You're certainly not going to hold it vertically. Hold it in such a way that your fingers are curling in the same direction as the current is curling. For me, I think I have to hold it this way, not this way, right? This way. What's north, X or Y? So let's go north pole at X, no. North pole at X, no. Now what that means is the magnetic field on the outside is going like that. What direction is the magnetic field inside the solenoid? Is it from X to Y or is it from Y to X? Yeah, from Y to X. No, no, yes, yes. Correct answer, C. Okay, here's a wire, and here is an external magnetic field. You know what? Magnetic field lines always point from what to what? What direction is that wire going to feel a force? I better draw in the current. Current is going this way, this way. Okay, current is going that way. Up, down, left, right. So, if you're stuck, I'll do mine up here. If you want to, hold your paper vertical to follow along with me. I would point my right thumb with the current. And I guess the magnetic field points from north to south. I think B. Yes? Yes?
What's going to his left?
And that's why I yelled at you right away. By the way, this is one of the few times lefties have an advantage, because as a lefty, I can hold my pen in my left hand while doing everything else. As a righty, you got to get rid of that pen. Do not. I've seen kids, they try and hold the pen while they're doing the right-hand rules. Well, of course, now their hand is in a different configuration from the way that I've taught you, and so things go wonky. Don't do that. You got to clear your hand free. This is how we can determine whether a charged object, a subatomic particle, is positive or negative. We send a stream of particles through an external magnetic field. So a beam of positively and negatively charged particles enters a magnetic field as shown. Which path illustrates the positive charge and which path illustrates the negative charge? Let's do the positives first. So we have positive charges. That's the same, that's mathematically like a current. Which way are the positive charges flowing? Both the positives and the negatives are flowing, right? But let's tackle the positives. That's easier. So point your right thumbs to the right. What direction do those X's mean? What direction is the B field, the magnetic field? So you're going to high-fi, extend your fingers into the page. Don't be doing this, Emily. If you get your hand like this. If as soon as you do that, you just introduced a 90-degree bend, and all your answers are going to be wrong. This is why I said for the right-hand motor rule, you want your hand as flat and level with your thumb sticking out. So, yes, fingers in, magnetic field into the page. What direction is the positive charges going to get deflected? Path I or path double I? Path I. These are positive. And negatives would be the other way. Correct answer? B. Example 15. An electron enters a uniform magnetic field as shown below. The path of the electron upon entering the field would be linear, circular. So, this is a bit of a trick question. Up until now, I've been very careful. I've made sure that the moving particles are traveling at right angles to the magnetic field. And what you're going to learn is the force on a moving charged particle only exists if that charged particle is cutting across magnetic field lines. If it's traveling parallel to magnetic field lines, no force exists. And you can try this if you want. Are you ready? Let's use this one up here at the front. We're all going to do this one, not on your piece of paper. Which way is this electron traveling? So that's the same as a proton traveling which way? So high five, thumb out. Everybody point your thumb to the left. What direction is this magnetic field? What's the picture? No, what direction is the magnetic field? Look at the picture. How can I, the only way is if I did that and I said that's not allowed. You have to have your thumb sticking out at a right angle, sticking out. I can't even do this mathematically with the right-hand rule. It doesn't work. I'd have to tuck my thumb in, which is a violation of our right-hand rule. When you get one that you just can't do with your hand, it's possible that no force is being applied. And in this case, because the electron is not cutting across magnetic field lines, it's going to keep going in a straight line at a steady speed. It's not going to feel a force. I have given you a gazillion of these to practice, and you need to try every single one of these for your homework. I've given you a whole bunch to practice here. Go to it, my angels.